Welcome back to our YouTube channel. Today we will talk more about calculator. An electronic calculator is typically a portable electronic device used to perform calculations, ranging from basic arithmetic to complex mathematics. The first solid-state electronic calculator was created in the early 1960s. Pocket-sized devices became available in the 1970s, especially after the Intel 4004, the first microprocessor, was developed by Intel for the Japanese calculator company Bizicom. Modern electronic calculators vary from cheap, giveaway, credit card-sized models to sturdy desktop models with built-in printers. They became popular in the mid-1970s as the incorporation of integrated circuits reduced their size and cost. By the end of that decade, prices had dropped to the point where a basic calculator was affordable to most and they became common in schools. Computer operating systems as far back as early Unix have included interactive calculator programs such as DC and Hawk, and Interactive Basic could be used to do calculations on most 1970s and 1980s home computers. Calculator functions are included in most smartphones, tablets, and personal digital assistant, PDA, type devices. In addition to general-purpose calculators, there are those designed for specific markets. For example, there are scientific calculators which include trigonometric and statistical calculations. Some calculators even have the ability to do computer algebra. Graphing calculators can be used to graph functions defined on the real line, or higher-dimensional Euclidean space. As of 2016, basic calculators cost little, but scientific and graphing models tend to cost more. With the very wide availability of smartphones and the like, dedicated hardware calculators, while still widely used, are less common than they once were. In 1986, calculators still represented an estimated 41% of the world's general-purpose hardware capacity to compute information. By 2007, this had diminished to less than 0.05%. Input. Electronic calculators contain a keyboard with buttons for digits and arithmetical operations. Some even contain 00 and 000 buttons to make larger or smaller numbers easier to enter. Most basic calculators assign only one digit or operation on each button. However, in more specific calculators, a button can perform multifunction working with key combinations. Display output. Calculators usually have liquid crystal displays, LCD, as output in place of historical light-emitting diode, LED, displays and vacuum fluorescent displays, VFD. Details are provided in the section Technical Improvements. Large-sized figures are often used to improve readability, while using decimal separator, usually a point rather than a comma, instead of or in addition to vulgar fractions. Various symbols for function commands may also be shown on the display. Fractions such as 1/3 are displayed as decimal approximations, for example rounded to 0.33333333. Also, some fractions, such as 1/7, which is 0.142857142857114, to 14 significant figures, can be difficult to recognize in decimal form. As a result, many scientific calculators are able to work in vulgar fractions or mixed numbers. Memory. Calculators also have the ability to save numbers into computer memory. Basic calculators usually store only one number at a time. More specific types are able to store many numbers represented in variables. The variables can also be used for constructing formulas. Some models have the ability to extend memory capacity to store more numbers. The extended memory address is termed an array index. Power source. Power sources of calculators are batteries, solar cells, or mains electricity. For old models, turning on with a switch or button. Some models even have no turn-off button, but they provide some way to put off, for example, leaving no operation for a moment, covering solar cell exposure, or closing their lid. Crank-powered calculators were also common in the early computer era. Key layout. The following keys are common to most pocket calculators. While the arrangement of the digits is standard, the positions of other keys vary from model to model. The illustration is an example. Calculator buttons and their meanings: MC or CM memory clear, MR, RM, or MRC memory recall, M memory subtraction, M plus memory addition, C or AC all clear, CE clear. Last entry, sometimes called CE/C, a first press clears the last entry, CE, a second press clears all, C. Plus or minus or CHS toggle positive/negative number aka change sign. %%. Divided by division. Times multiplication. Subtraction. Plus addition. Decimal point. Square root. Equals result. In general, a basic electronic calculator consists of the following components: power source, mains electricity, battery, and or solar cell. Keypad, input device, consists of keys used to input numbers and function commands, addition, multiplication, square root, etc. Display panel, output device, displays input numbers, commands, and results. Liquid crystal displays, LCDs, vacuum fluorescent displays, VFDs, and light-emitting diode, LED, displays use 7 segments to represent each digit in a basic calculator. Advanced calculators may use dot matrix displays. A printing calculator, in addition to a display panel, has a printing unit that prints results in ink onto a roll of paper, using a printing mechanism. Processor chip, microprocessor or central processing unit. Example: a basic explanation as to how calculations are performed in a simple 4-function calculator. To perform the calculation 25 plus 9, one presses keys in the following sequence on most calculators: 25 plus 9 equals. When 25 is entered, it is picked up by the scanning unit. The number 25 is encoded and sent to the X register. Next, when the plus key is pressed, the addition instruction is also encoded and sent to the flag or the status register. The second number 9 is encoded and sent to the X register. This shifts, the first number out into the Y register. When the equals key is pressed, a signal, from the flag or status register tells the permanent or non-volatile memory that the operation to be done is addition. The numbers in the X and Y registers are then loaded into the ALU and the calculation is carried out following instructions from the permanent or non-volatile memory. The answer, 34, is shifted, back to the X register. From there, it is converted by the binary decoder unit into a decimal number, usually binary coded decimal, and then shown on the display panel. Other functions are usually performed using repeated additions or subtractions. Most pocket calculators do all their calculations in binary coded decimal, BCD, rather than binary. BCD is common in electronic systems where a numeric value is to be displayed, especially in systems consisting solely of digital logic, and not containing a microprocessor. By employing BCD, the manipulation of numerical data for display can be greatly simplified by treating each digit as a separate single sub-circuit. This matches much more closely the physical reality of display hardware. A designer might choose to use a series of separate identical 7-segment displays to build a metering circuit, for example. If the numeric quantity were stored and manipulated as pure binary, interfacing to such a display would require complex circuitry. Therefore, in cases where the calculations are relatively simple, working throughout with BCD can lead to a simpler overall system than converting to and from binary. For example, CDs keep the track number in BCD, limiting them to 99 tracks. The same argument applies when hardware of this type uses an embedded microcontroller or other small processor. Often, smaller code results when representing numbers internally in BCD format, since a conversion from OR to binary representation can be expensive on such limited processors. For these applications, some small processors feature BCD arithmetic modes, which assist when writing routines that manipulate BCD quantities. Where calculators have added functions, such as square root, or trigonometric functions, software algorithms are required to produce high-precision results. Sometimes significant design effort is needed to fit all the desired functions in the limited memory space available in the calculator chip, with acceptable calculation time. The first mainframe computers, using firstly vacuum tubes and later transistors in the logic circuits, appeared in the 1940s and 1950s. This technology was to provide a stepping stone to the development of electronic calculators. The Casio Computer Company, in Japan, released the Model 14, a calculator in 1957, which was the world's first all-electric, relatively, compact calculator. It did not use electronic logic but was based on relay technology, and was built into a desk. In October 1961, the world's first all-electronic desktop calculator, the British Bell Punch/Sumlock Comptometer Anita, a new inspiration to arithmetic/accounting, was announced. 1718 This machine used vacuum tubes, cold cathode tubes, and decatrons in its circuits, with 12 cold cathode Nixie tubes for its display. Two models were displayed, the Mk7 for continental Europe and the Mk8 for Britain and the rest of the world, both for delivery from early 1962. The Mk7 was a slightly earlier design with a more complicated mode of multiplication, and was soon dropped in favor of the simpler Mark 8. The Anita had a full keyboard, similar to mechanical comptometers of the time, a feature that was unique to it and the later Sharp CS10A among electronic calculators. The Anita weighed roughly 33 pounds, 15 kilograms, due to its large tube system. Bell Punch had been producing key-driven mechanical calculators of the comptometer type under the names Plus and Sumlock, and had realized in the mid-1950s that the future of calculators lay in electronics. They employed the young graduate Norbert Kitz, who had worked on the early British Pilot Ace computer project, to lead the development. The Anita sold well since it was the only electronic desktop calculator available, and was silent and quick. The tube technology of the Anita was superseded in June 1963 by the US-manufactured Friden EC130, which had an all-transistor design, a stack of four 13-digit numbers displayed on a 5-inch, 13 cm, cathode ray tube, CRT, and introduced reverse Polish notation, RPN, to the calculator market for a price of $2,200, which was about 3 times the cost of an electromechanical calculator of the time. Like Bell Punch, Friden was a manufacturer of mechanical calculators that had decided that the future lay in electronics. In 1964 more all-transistor electronic calculators were introduced. Sharp introduced the CS10A, which weighed 25 kilograms, 55 pounds, and cost 500,000 yen, $4,555.81, and Industria Macchine Elettronica of Italy introduced the IME84, to which several extra keyboard and display units could be connected so that several people could make use of it, but apparently not at the same time. The Victor 3900 was the first to use integrated circuits in place of individual transistors, but production problems delayed sales until 1966. There followed a series of electronic calculator models from these and other manufacturers, including Canon, Mathetronics, Olivetti, SCM, Smith Corona Marchant, Sony, Toshiba, and Wang. The early calculators used hundreds of germanium transistors, which were cheaper than silicon transistors, on multiple circuit boards. Display types used were CRT, cold cathode Nixie tubes, and filament lamps. Memory technology was usually based on the delay line memory or the magnetic core memory, though the Toshiba Toscal BC1411 appears to have used an early form of dynamic RAM built from discrete components. Already there was a desire for smaller and less power-hungry machines. Bulgaria's Elka 6521, introduced in 1965, was developed by the Central Institute for Calculation Technologies and built at the Electronica factory in Sofia. The name derives from Elektronen calculator, and it weighed around 8 kilograms 18 pounds. It is the first calculator in the world which includes the square root function. Later that same year were released the Elkit 22, with a luminescent display, and the Elkit 25, with an built-in printer. Several other models were developed until the first pocket model, the Elka 101, was released in 1974. The writing on it was in Roman script, and it was exported to Western countries. The first desktop programmable calculators were produced in the mid-1960s. They included the Mathitronix Mothatron, 1964, and the Olivetti Programma 101, late 1965, which were solid-state, desktop, printing, floating point, algebraic entry, programmable, stored program electronic calculators. Both could be programmed by the end user and print out their results. The Programma 101 saw much wider distribution and had the added feature of offline storage of programs via magnetic cards. Another early programmable desktop calculator, and maybe the first Japanese one, was the Casio AL1000, produced in 1967. It featured an Nixie tubes display and had transistor electronics and ferrite core memory. The Monroe EPIC programmable calculator came on the market in 1967. A large, printing, desktop unit, with an attached floor-standing logic tower, it could be programmed to perform many computer-like functions. However, the only branch instruction was an implied unconditional branch, goto, at the end of the operation stack, returning the program to its starting instruction. Thus, it was not possible to include any conditional branch, if-then-else, logic. During this era, the absence of the conditional branch was sometimes used to distinguish a programmable calculator from a computer. The first Soviet programmable desktop calculator Iskra 123, powered by the power grid, was released at the start of the 1970s. 1970s to mid-1980s. The electronic calculators of the mid-1960s were large and heavy desktop machines due to their use of hundreds of transistors on several circuit boards with a large power consumption that required an AC power supply. There were great efforts to put the logic required for a calculator into fewer and fewer integrated circuits, chips, and calculator electronics was one of the leading edges of semiconductor development. U.S. semiconductor manufacturers led the world in large-scale integration, LSI, semiconductor development, squeezing more and more functions into individual integrated circuits. This led to alliances between Japanese calculator manufacturers and U.S. semiconductor companies, Canon Incorporated with Texas Instruments, Hayakawa Electric, later renamed Sharp Corporation, with North American Rockwell Microelectronics, later renamed Rockwell International, Visicom with Mistec and Intel, and General Instrument with Sanyo. Pocket calculator. By 1970, a calculator could be made using just a few chips of low power consumption, allowing portable models powered from rechargeable batteries. The first handheld calculator was a 1967 prototype called Caltech, whose development was led by Jack Kilby at Texas Instruments in a research project to produce a portable calculator. It could add, multiply, subtract, and divide, and its output device was a paper tape. As a result of the Caltech project, Texas Instruments was granted master patents on portable calculators. The first commercially produced portable calculators appeared in Japan in 1970, and were soon marketed around the world. These included the Sanyo ICC0081 mini calculator, the Canon Pocketronic, and the Sharp QT8B Micro Compot. The Canon Pocketronic was a development from the Caltech project. It had no traditional display, numerical output was on thermal paper tape. Sharp put in great efforts in size and power reduction and introduced in January 1971 the Sharp L8, also marketed as the Facet 1111, which was close to being a pocket calculator. It weighed 1.59 pounds, 721 grams, had a vacuum fluorescent display, rechargeable NiCad batteries, and initially sold for $395. However, Integrated circuit development efforts culminated in early 1971 with the introduction of the first calculator on a chip, the MK6010 by mistake, followed by Texas Instruments later in the year. Although these early handheld calculators were very costly, these advances in electronics, together with developments in display technology, such as the vacuum fluorescent display, LED, and LCD, led within a few years to the cheap pocket calculator available to all. In 1971, Pico Electronics and General Instrument also introduced their first collaboration in ICS, a full single-chip calculator IC for the Monroe Royal Digital 3 calculator. Pico was a spin-out by 5 GI design engineers whose vision was to create single-chip calculator ICS. Pico and GI went on to have significant success in the burgeoning handheld calculator market. The first truly pocket-sized electronic calculator was the Bizicom LE120A Handy, which was marketed early in 1971. Made in Japan, this was also the first calculator to use an LED display, the first handheld calculator to use a single integrated circuit, then proclaimed as a calculator on a chip, the Mistec MK6010, and the first electronic calculator to run off replaceable batteries. Using 4A size cells, the LE120A measures 4.9 by 2.8 by 0.9 inches, 124 mm x 71 mm x 23 mm. The first European-made pocket-sized calculator, DB800, was made in May 1971 by Digitron in Buj, Croatia, former Yugoslavia, with 4 functions and an 8-digit display and special characters for a negative number and a warning that the calculation has too many digits to display. The first American-made pocket-sized calculator, the Bomar 901B, popularly termed the Bomar Brain, measuring 5.2 by 3.0 by 1.5 inches, 132 mm x 76 mm x 38 mm, came out in the autumn of 1971, with 4 functions and an 8-digit red LED display, for $240, while in August 1972 the 4-function Sinclair Executive became the first slimline pocket calculator measuring 5.4 by 2.2 by 0.35 inches, 137.2 mm x 55.9 mm x 8.9 mm, and weighing 2.5 ounces, 71 g. It retailed for around £79, $194 at the time. By the end of the decade, similar calculators were priced less than £5, $6.85. Following protracted development over the course of 2 years, including a botched partnership with Texas Instruments, Eldorado Electrodata released 5 pocket calculators in 1972. One, called the Touch Magic, was no bigger than a pack of cigarettes according to administrative management. The first Soviet Union-made pocket-sized calculator, the Electronica B3-04, was developed by the end of 1973 and sold at the start of 1974. One of the first low-cost calculators was the Sinclair Cambridge, launched in August 1973. It retailed for £29.95, $41.03, or £5, $6.85, less in kit form. The Sinclair calculators were successful because they were far cheaper than the competition. However, their design led to slow and inaccurate computations of transcendental functions. Scientific pocket calculators. Meanwhile, Hewlett-Packard, HP, had been developing a pocket calculator. Launched in early 1972, it was unlike the other basic 4-function pocket calculators then available in that it was the first pocket calculator with scientific functions that could replace a slide rule. The $395 HP 35, along with nearly all later HP engineering calculators, uses reverse Polish notation, RPN, also called postfix notation. A calculation like 8 plus 5 is, using RPN, performed by pressing 8, enter upward arrow, 5, and plus, instead of the algebraic infix notation, 8, plus, 5, equals. It had 35 buttons and was based on Mistec MK6020 chip. The first Soviet scientific pocket-sized calculator, the B3-18, was completed by the end of 1975. In 1973, Texas Instruments, TI, introduced the state root 10, SR signifying slide rule, an algebraic entry pocket calculator using scientific notation for $150. Shortly after, the state root 11 featured an added key for entering pi. It was followed the next year by the state root 50, which added log and trig functions to compete with the HP35, and in 1977 the mass-marketed TI-30 line, which is still produced. In 1978, a new company, Calculated Industries, arose which focused on specialized markets. Their first calculator, the Lone Arranger, 1978, was a pocket calculator marketed to the real estate industry with pre-programmed functions to simplify the process of calculating payments and future values. In 1985, CI launched a calculator for the construction industry called the Construction Master, which came pre-programmed with common construction calculations, such as angles, stairs, roofing math, pitch, rise, run, and feet-inch fraction conversions. This would be the first in a line of construction-related calculators. The first programmable pocket calculator was the HP65. In 1974, it had a capacity of 100 instructions, and could store and retrieve programs with a built-in magnetic card reader. 2 years later, the HP25C introduced continuous memory, i.e., programs and data were retained in CMOS memory during power off. In 1979, HP released the first alphanumeric, programmable, expandable calculator, the HP41C. It could be expanded with random access memory, RAM, for memory, and read-only memory, ROM, for software, modules, and peripherals like barcode readers, microcassette and floppy disk drives, paper roll thermal printers, and miscellaneous communication interfaces, RS-232, HPIL, HPIB. The first Soviet pocket battery-powered programmable calculator, Electronica B3-21, was developed by the end of 1976 and released at the start of 1977. At the start of the 1970s, handheld electronic calculators were very costly, at 2 or 3 weeks' wages, and so were a luxury item. The high price was due to their construction requiring many mechanical and electronic components which were costly to produce, and production runs that were too small to exploit economies of scale. Many firms saw that there were good profits to be made in the calculator business with the margin on such high prices. However, the cost of calculators fell as components and their production methods improved, and the effect of economies of scale was felt. By 1976, the cost of the cheapest 4-function pocket calculator had dropped to a few dollars, about 1/20th of the cost 5 years before. The results of this were that the pocket calculator was affordable, and that it was now difficult for the manufacturers to make a profit from calculators, leading to many firms dropping out of the business or closing. The firms that survived making calculators tended to be those with high outputs of higher quality calculators, or producing high-specification scientific and programmable calculators. The first calculator capable of symbolic computing was the HP28C, released in 1987. It could, for example, solve quadratic equations symbolically. The first graphing calculator was the Casio FX7000G, released in 1985. The two leading manufacturers, HP and TI, released increasingly feature-laden calculators during the 1980s and 1990s. In most countries, students use calculators for schoolwork. There was initial resistance to the idea out of fear that basic or elementary arithmetic skills would suffer. There remains disagreement about the importance of the ability to perform calculations in the head, with some curricula restricting calculator use until a certain level of proficiency has been obtained, while others concentrate more on teaching estimation methods and problem solving. Research suggests that inadequate guidance in the use of calculating tools can restrict the kind of mathematical thinking that students engage in. Others have argued that calculator use can even cause core mathematical skills to atrophy, or that such use can prevent understanding of advanced algebraic concepts. In the United States, many math educators and boards of education have enthusiastically endorsed the National Council of Teachers of Mathematics, NCTM, standards and actively promoted the use of classroom calculators from kindergarten through high school. Personal computers often come with a calculator utility program that emulates the appearance and functions of a calculator, using the graphical user interface to portray a calculator. Examples include the Windows Calculator, Apple's Calculator, and KDE's KCalc. Most personal data assistants, PDAs, and smartphones also have such a feature. The fundamental difference between a calculator and computer is that a computer can be programmed in a way that allows the program to take different branches according to intermediate results, while calculators are pre-designed with specific functions, such as addition, multiplication, and logarithms, built in. The distinction is not clear-cut. Some devices classed as programmable calculators have programming functions, sometimes with support for programming languages, such as RPL or TI Basic. For instance, instead of a hardware multiplier, a calculator might implement floating-point mathematics with code in read-only memory, ROM, and compute trigonometric functions with the Cordic algorithm because Cordic does not require much multiplication. Bit serial logic designs are more common in calculators, whereas bit parallel designs dominate general-purpose computers, because a bit serial design minimizes chip complexity, but takes many more clock cycles. This distinction blurs with high-end calculators, which use processor chips associated with computer and embedded systems design, more so the Z80, MC68000, and ARM architectures, and some custom designs specialized for the calculator market. Thank you for watching this video, so much more to come.